This problem says I have an 8 kilogram block that is moving with an initial speed of 6 meters per second on a rough horizontal surface. If the force of friction is 12 newtons, approximately how far does the block travel before it stops? Alright, so our force is 12 newtons, and that's the only force acting on it that we care about, because we have our object, and we have the force of gravity down, we have the normal force, and we have the frictional force. And some people are tempted to say, well, what about the force that's making it go forward? There doesn't have to be any force making it go forward. It has a velocity going forward, but an object in motion remains in motion unless a force acts on it. So there's no force pushing it forward, just a force slowing it down. And that's the frictional force. And so that is our net force. So our net force is 12. And that will equal our mass times our acceleration, or 12 equals 8a, or a equals 12 over 8, which is 3 over 2, or 1.5 meters per second squared, and that's in the opposite direction that it's moving. So if it's moving positive 6 meters per second, the acceleration has to be negative 1.5 meter per second squared, because the friction always acts opposite the direction of motion. So we have acceleration is minus 1.5 meters per second squared. And the question is, how far does the block travel before it comes to a stop? So here we want to use a kinematic equation, and the kinematic equation that works the best is the one that has that our final velocity squared equals our initial velocity squared plus 2a delta x, because that's what we're looking for, is delta x. So when it comes to a stop, that would mean our final velocity is 0 meters per second. So 0 meters per second squared equals 6 meters per second squared plus 2 times negative 1.5 delta x, negative 1.5 meter per second squared, or negative 36 meters squared over second squared equals negative 3 meters per second squared delta x. If you just divide both sides by negative 3 meters per second squared, you get that delta x equals 12 meters. And that would be the answer to that one. And then I think I have time to do one more. I'll pick a good one. Oh, I just noticed that number 28, if you go back and look at the video that I did before that talks about acceleration on the surface of a planet, that would be on number 28, so if you look at the previous video. Okay, I'm going to do 29, which has a plane is traveling at 200 meters per second following the arc of a vertical circle of radius r. And it's traveling at 200 meters per second. This is number 28. 29. At the top of its path, the passengers experience weightlessness. To one significant figure, what is the value of R? So if I'm a passenger there, I have several forces acting on me. So I have the force of gravity down, and I have the normal force up, and to experience weightlessness happens when the normal force is 0. So we know that the centripetal force is mv squared over r, or the centripetal force is m 200 meters per second squared over r. And we know that that has to equal the force due to gravity in order for the normal force to be 0, because that would mean, so we need the net force towards the center, we need the net force to be just the force due to gravity, because we want the normal force to be 0. And it's the net force that provides the centripetal force. And so the net force equals the centripetal force, and we need that to be equal to the force due to gravity, because we need our normal force to be 0 in order to experience weightlessness. And so the force due to gravity is mg. So our m's cancel, and we're solving for r, so multiply both sides by r, and you get that 200 meters per second squared over g equals r, and so that would be 40000 meters squared second squared, and we'll just have g be 10 meters per second squared. So the second squareds cancel, and meters cancel, and I get 4,000 meters. And I think I have to stop there.